Section 4.8 is on antiderivatives and differential equations, but that's going to really just be an extension of this conversation about antiderivatives. So that's what we're going to start with here. And it really is what it sounds like to you, most likely, which is anti, kind of the opposite of, and then the derivative. So we're trying to think of a function whose derivative is what's given. So in this first example, we're trying to think of a function, and we're going to refer to that function as capital F, whose derivative is lowercase f, which is this function 4x cubed. So no doubt if we were in class and I asked some students to kind of think about this, just for a second or so, it doesn't take long before students are pretty easily able to come up with, well, what about just x to the fourth? So if capital F is x to the fourth, then the idea is here, if I run a little check and I take the derivative of that capital F, I certainly get back to 4x cubed. So it works. Then I'd say, well, are there any other functions? And typically, there's a little bit of a pause and it just takes maybe a minute or so before students realize, well, there could have, I guess, also been a constant, right? Like we could have had, get my pen back here, it could have also had capital F of x could have been x to the fourth minus 3. Or it could have had any other arbitrary constants that is added or subtracted. So a lot of times we will generically refer to that as a plus c. And in all of these situations, if you were to take the derivative of these, you get back to 4x cubed. So all of these are what we would call antiderivatives. When you write it in terms of the plus c, that's going to be what this book calls the general form, or what other books might call the family of antiderivatives. So our definition is a function capital F is the antiderivative of lowercase f if when you take, and we have a typo here that we need to fix, if when we take the derivative, and this is right from your book, but when you take the derivative of capital F prime, so this should be capital F prime here, not lowercase f. So if when you take the derivative of capital F, you get back to lowercase f, then capital F is called the antiderivative of lowercase f. And then if you have this whole family of antiderivatives, the plus c, that's what we call the general form. All right, so let's look at another example. So again, right now, just trying to kind of reason your way through and think about these just from a logical perspective. So if I gave you a function lowercase f is equal to 6x, I'd ask you to think for a couple of seconds, can you work, your power rules and constants backwards? So hopefully, after a couple minutes, you could pause if you want to think for just a second longer, but that would come out to be 3x squared. Again, if you were to check that and take the derivative there of capital F, you would get back to 6x. And again, the more general form that we would really want to go with would be the plus c on that. Okay, so now what we want to do is we want to, instead of just kind of like thinking and reasoning and trying to go backwards, let's try to solidify some rules here for some of our basic antiderivatives. All right, so the first one, if you have k as a constant here, then the antiderivative of a constant is going to be that constant times x, and all of these are going to have this plus c at the end. Now, the power rule, kind of what we're working here and kind of what you were thinking about critically as you worked these last two examples backwards, when you think about the power rule for the derivative, it's kind of multiplying by the power first and then decreasing the power by 1. So we're going to do the opposite thing in the opposite order. So the first thing we're going to do is we're going to increase the power by 1. So the first thing we're going to do is we're going to add 1 to that power. And then instead of multiplying by the power, we're going to do the opposite, which is going to be to divide by the power. So we're going to have x to the n plus 1 divided by n plus 1. Or, of course, if you want to, a lot of times we might bring this out kind of as a constant, like the 1 over n plus 1, and then times the x to the n plus 1. And then always plus this arbitrary constant. Now, this is good for every power except for when n is equal to negative 1, because, of course, you can see if n was equal to negative 1, right here, you would be dividing by 0, and division by 0 is not defined. So that kind of begs the question, well then, what is the antiderivative of, if we have a power of negative 1, of x to the negative 1? So you're thinking back to the first kind of part of the course, well, what was the function that you learned whose derivative was 1 over x? And hopefully that comes back to you, that was your natural log function. But we do have an extra, instead of just natural log of x, we have a little extra thing we got to do here. It's going to be natural log of the absolute value of x. And kind of the reason is over here in the original, this 1 over x, obviously if you're starting off with 1 over x, the only thing that x can't be is 0. But x could be negative or x could be positive, it just can't be 0. The problem is then if you go to then take the antiderivative and you only wrote it as natural log of x, and x was negative, this would be a problem because logs are only defined for positive values. So if x was negative and we just had natural log of x, that would be undefined. So we address that by just taking the absolute value. So that's kind of one way to think about it. There's other explanations, but that's one way to just kind of understand what might be going on there. Okay, so let's keep this going. So here's what you know about trig functions. So here's what I would like you to kind of think about. So let's kind of write this off to the side here. So let's just recall from the first part of the course, you know the derivatives of the 6 trig functions. So sine, cosine, tangent, cotangent, secant, and cosecant. So you know that their derivatives are cosine, and then the opposite of sine, secant squared, the opposite of cosecant squared, secant tangent, and minus cosecant x, cotangent x. And so what you know here is you know how to take these derivatives, right? So this is what you already know. And that is going from here to here, from this column to this column. These are your derivatives that you already know. So that means you know these 6 antiderivatives. So you know these antiderivatives in reverse. So this isn't really like an equality here, but it is just kind of thinking about going from one to the other. So maybe I'll just sort of draw a line here. So this is what I would like you, as you're kind of thinking about these 6 rules. These are kind of the special 6 that you already knew from the first half of the course. We're just applying them in reverse. All right, so now going from the right column back to the left column. So the antiderivative of cosine going from the right to the left is going to be sine of x plus c. The antiderivative, again, going from the right to the left, well, we know the antiderivative of minus sine x is equal to cosine, and then we know that a constant multiple essentially is going to get carried along. So this is going to end up giving you the opposite of cosine of x. And so again, if you weren't sure on this, like let's check this one, this whole notion with the negative there. If you were to take this derivative, when I was saying that the sign gets carried along, let's think about that with the check here. The negative gets carried along, and then the derivative of cosine is minus sine. And so those two negatives become positive, and I do get back to just sign, which is what we started with. So let's continue here and just sort of write these out. All right, so secant squared, its antiderivative, going from the right side to the left, remember, that's your tangent of x plus c. Negative cosecant squared, if you kind of isolate for the cosecant squared, again, kind of that check we just did, this is going to give us the minus cotan of x plus c. Antiderivative of secant x tangent x is going to be secant of x plus c. And then the last one is going to be cotangent is going to be minus your cosecant of x plus c. All right, let's keep going. I just want to get this list kind of established for ourselves here. The next three involve your inverse trig function. So again, hopefully these are familiar. So the antiderivative then of 1 over the square root of 1 minus x squared, that is your arc sine of x, or sine inverse if you prefer, plus c. 1 over 1 plus x squared, that antiderivative is your arctan, or tan inverse if you prefer, of x plus c. And then the last one is your arcsecant of x, or secant inverse, plus c. And then the last couple, this one's not too surprising, right? Derivative of e to the x is e to the x, so is its antiderivative. And then the last one for a base other than e, its antiderivative, and this one might require us, because we are kind of adjusting by this constant. So I'm just going to write it out, and then let's, again, let's think about running, on a lot of these, on any of these, you could run, your check. So if we were to show maybe the check on this one, if you were to take your capital F prime, 1 over natural log of a would get carried along as a constant multiple, and if you remember, the derivative of a to the x is a to the x times natural log of a. And so these natural log of a's would reduce, and you would just be left with your a to the x. So if we kind of check that one, that should, and you can do that on any of these, of course, that's the whole idea here. All right, so when we come back next time, we're going to look at some examples using these antiderivative rules.